bad. So, as I said, I was going to start with the alkylating agents, but since I've given you an assignment on the alkylating agents, please work on them quickly, very quickly. Then we have the assignment, and then we'll go back and look at them. And we want to start with the anti-metabolites. I think I had a span which was slightly smaller than this. Yes, we want to start with the anti-metabolites. And we've already said that the anti-metabolites are compounds closely related in structure to a cellular precursor molecule, so that they do what we call competitive inhibition, structural similarity, and therefore there can be an exchange of one with the other. Antimetabolites are capable of preventing the proper use or formation of the normal cellular product, like if you're looking at a DNA, if you're looking at a structural protein, if you're looking at an enzyme. Those are the ones we're calling normal cellular products in a manner sufficient to alter the outcome of that pathway. So they bind. You are supposed to be making a certain enzyme, which is supposed to have, let's say, 20 amino acids. One, you have a fraudulent amino acid. The fraudulent amino acid, or the amino acid which has a slightly different structure, is taken up. If it's taken up when the enzyme synthesis is at position, let's say 12, you require another 8 amino acids. Then the minute you take the fraudulent amino acid, it gets into the system. It gets into the chain. You cannot continue. Termination. So your resultant enzyme will have, let's say, 12 amino acids, and one of the amino acids will also be defective. So what you get, sometimes you get fraudulent enzymes, and some of those fraudulent enzymes are even toxic. They bring about toxic effects within the bacteria, within the virus, and therefore kill the virus. So that's what we're saying when we talk about them affecting normal cellular products, and of course altering the outcome. Most antimetabolites are effective cancer chemotherapeutic agents. Their interaction with the biosynthesis of the nucleic acids, the antimetabolites hamper the production of either DNA or RNA by a variety of mechanisms, which mainly include competition for binding sites. So as competitive inhibitors, they have structural similarity with the endogenous substrate, and therefore they will go for the same site. And once they go for the same site and they are preferentially bound, they will stop the process. So the competition for the binding sites of enzymes that participate in essential biosynthetic processes, be it synthesis of enzymes, be it of RNA, be it of DNA, and so on, incorporation. So one of them is competitive inhibition, fighting for the site. So please note they are different. These are different. One, they are competing for the same site. Two, they are incorporated. So so after they compete for the site, then they are bound. Incorporation is the nucleic acid, which inhibits their normal function and triggers their apoptosis process. So the first one is they compete for the same site. And once they are picked up, the process stops. Then another one, and sometimes they can be incorporated and the process continues. But the resultant DNA is fraudulent. It is not the right one, or the resultant product cannot do the normal functions. Most of the targeted enzymes and processes are involved in the regulatory steps of cell division and cell tissue growth. That again we have discussed. Often the administered drugs actually are prodrugs. So this is important for us to note. And most of these drugs are prodrugs. You give them as prodrugs. You can give them, as we said last time, as a base. You can give it as a nucleoside or as a nucleoside. So even when it goes in as a base or the nucleoside, it is still a prodrug, because more often than not, they are first changed either to the nucleus, they usually change the nucleotide. And now the nucleotide is the final product that is taken up for synthesis of the nucleic acid. So usually they are prodrugs, and they must be activated in the body not through metabolism in this case, but through catabolism, whereby they are built up to bigger molecules. So often a product form of an antimetabolic activation in vivo to use the active inhibitor. Purine and pyrimidine antimetabolites require the formation of the nucleoside, and finally the corresponding nucleotide, as we have said. So of course, if you have the pyrimidine and purine bases, those are bases. So first they will go to the nucleoside, addition of the ribose sugar, and then they will go into the nucleotide. Now when it has the 3 units, it has the base, it has the sugar, and it has the phosphate. So once it becomes the nucleotide, it is now ready to be taken up. But since it has a different structure, it will be an antimetabolite. An antimetabolite and its transformation products may inhibit several different enzymes involved in tissue growth that we already said. The purine and pyrimidine antimetabolites compounds are often incorporated into nucleic acids and the nucleic acid polymers. So incorporated either into nucleic acids or the DNA and RNA. So once you get the nucleic acid, like let's say uridylic acid, the uridylic acid is then incorporated into the DNA to give you the DNA polymer. The minute it's inside there, either there will be stoppage of the formation of the DNA or that will act as a fraudulent molecule and therefore not give you what you expect. These substances are generally self-specific with activity in S phase. We've already mentioned about specificity of drugs in terms of the cell cycle. So we are saying these ones are S phase specific. Then we also have, so we have those two, the purines and the pyrimidines, but we also have the antifolates. These are compounds designed to interact at cofactor sites for enzymes involved in the biosynthesis of nucleic acid bases. Again, we are going to see this in details. We are talking about the tetrahydrofolate cofactor, which we require for, again, the synthesis of bases and purines. The biosynthesis of these nucleic acid bases depends heavily on the ability of folate cofactors. You must have them. Hence, antimetabolites of the folate find utility as antineoplastic agents. So the cofactors, which are derivatives of folic acid, are important in the synthesis of purines and bases. So, again, ultimately, they will block the synthesis of the purine and the bases. So we can't classify them, therefore, depending on what they influence, the antimetabolites, antineoplastics are categorized by the class of nucleotide they inhibit. And again, we have talked about they can be purine antagonists, which inhibit the synthesis of purine-based nucleotide adenylate monophosphate, which is AMP, and guanylate monophosphate, that is GMP. So they will have an influence on the synthesis of AMP and also GMP. Those are the two purines, GMP. Remember, we start with AMP and then it is built to DMP and then TMP. The adenine monophosphate, then it is moves to ADP and then ATP on addition of the phosphates. Pyrimidine antagonists inhibit the production of pyrimidine-based nucleotides, primarily the deoxythymidine monophosphate, and mainly it is based nucleotides, primarily the deoxythymidine monophosphate, DTMP, example, the folate antagonist. This is because the deoxy TMP or the TMP, the thymine, is made from the uracil. And for it to be made from the uracil, you require the folate cofactors. So remember, TMP is made from uracil, and for you to make it, you require the folate, the folate cofactors. So if you do not have the folate cofactors, then again, you will not be able to make your pyrimidines. We are looking at pyrimidine antagonists, and the first category we can look at is the dihydrofolate reductase inhibitors. So dihydrofolate reductase inhibitors, remember, when you are synthesizing folic acid, when these microorganisms are synthesizing folic acid, if you just have a reflection, you first have the first enzyme, which is the dihydrofolate synthase. It works twice. In two steps, dihydrofolate synthase. Once you form your dihydrofolate, or you form your dihydropteroic acid or dihydrofolic acid, the dihydrofolic acid still does not work until it is converted to tetrahydrofolic acid. So the tetrahydrofolic acid to be produced from dihydrofolic acid, remember, you require the reductase enzyme. So you require the dihydrofolate reductase enzyme because it is reducing the dihydrofolic acid to tetrahydrofolic acid. So that enzyme, the dihydrofolate reductase enzyme, is the one you are blocking by denying it the cofactors that it requires. Once you block that enzyme, it means the dihydrofolic acid will not be. But you're blocking that enzyme, a dihydrofolic reductase enzyme. Once you block it, it means the dihydrofolic acid will not be converted to the tetrahydrofolic acid, and therefore you require the tetrahydrofolic acid for the synthesis of thymine from uracil, which means then you will not synthesize your pyrimidines. You also require that cofactor, the tetrahydrofolic acid, also for synthesis of purines. When you're doing the basic structure of the purines, the 6-membered ring of the purines, the basic structure, you also require the tetrahydrofolic acid. Therefore, you will not synthesize your purines, you will not synthesize your pyrimidines again. If you lack those precursors, then you will not synthesize. You will not ultimately synthesize your DNA. We are therefore saying the dihydrofolate reductase enzyme is crucial in maintaining levels of the enzyme cofactor tetrahydrofolate, or which is usually given FH4, tetrahydrofolic acid. The tetrahydrofolate cofactor is needed for the synthesis of the DNA building blocks, deoxythymidylate monophosphate, and ultimately DNA synthesis. Just what I've explained. The DHFR, the dihydrofolate reductase enzyme, catalyzes the reduction of the vitamin folic acid to FH4 in 2 steps via dihydrofolate. So you start with dihydrofolate, and then it will catalyze the reduction of dihydrofolate to FH4. The FH4 picks up a single carbon unit to form the N5, N10 methylene tetrahydrofolate. So this is very important. So that this F4 is behaving as a cofactor. It will pick a methylene group, an extra carbon atom, to give us the N5, N10 methylene tetrahydrofolate, which then acts as a source of 1 carbon unit for various biosynthetic pathways, including the methylation of deoxyuridine monophosphate to give us the deoxythymidine monophosphate. So remember, the uridine monophosphate is okay for RNA, but without TMP, you cannot form DNA. And of course, you do require the DNA in the host cells. The N5, N10 methylene FH4 is converted back to the dihydrofolate. So that is the 5, N5, N10. That is a cofactor. The FH4 carrying, this is actually a 1 carbon moiety carrier, is converted back to the dihydrofolate in the process, and the dihydrofolate reductase is vital in restoring the N5, N10 methylene for further reaction. So what we are saying is that once you have the N5, N10 methylene tetrahydrofolate, it donates its N5, N10. It donates actually that 1 carbon. And once it donates that 1 carbon, it's changed directly to the dihydrofolic acid, and that dihydrofolic acid again now can continue the process, again changed to the tetrahydrofolic, and then from the tetrahydrofolic again changed, it carries the carbon moiety. What is important to note here is that when the cofactor, the N5, N10 tetrahydrofolic loses the carbon moiety, it does not go to FH4. That's what is very important to note. That on losing the 1 carbon moiety, it does not go to FH4. It goes to FH2. So unfortunately, you will not have any FH4. It goes to FH2, must be acted on by the dihydrofolate reductase enzyme. So if you have blocked the dihydrofolate reductase enzyme, you are not having any FH4 generated in the process of making the purines and the pyrimidines. The FH4 is reduced automatically to FH2, so it has to be acted on. So this makes it a bit even more complex. It even further squeezes the availability of FH4, because if on conversion of N5, N10 methylene FH4, you get FH4, at least you'll be having some FH4 in the circulation. But the N5, N10 methylene FH4 is converted to FH2, put back into the system, must be acted by the dihydrofolate reductase enzyme to regenerate the FH4. And then the FH4 is to pick one carbon moiety, and then that one carbon moiety or that cofactor carrying the one carbon moiety will deliver that one carbon moiety to either the purine, which is growing, or to the uracil to give you thymidine, and the process continues. So I hope you have understood that process. So that is what I'm illustrating here. So remember, we did mention the methotrexate is, of course, folate anti-metabolite. So you are saying folic acid, dihydrofolate, dihydrofolate reductase, folic acid, it is reduced fast by the dihydrofolate reductase to the FH2, and then again the hydrofolate reductase to FH4, and then now the FH4 picks the methylene group to give you the N5, N10 methylene FH4. This is a cofactor you require so much for synthesis of purines and even many other metabolic processes. So that is picked. You have a uracil molecule, a deoxyuridine redylate monophosphate, and that must pick the methyl group from the N5, N10 methylene FH4, and you see it goes back to FH2. But fortunately, using the enzyme thymidylate synthetase, it gives you the DTMP. Gives you the DTMP. And now the DTMP converted to deoxy TDP, and then the deoxy TDP, deoxy T, you have T triphosphate, so TTP, then that is used in the synthesis of the nucleic acid. We will see also the 5-fluorouracil here, which is also an antimetabolite, can also now directly block that enzyme. So we're only saying in this particular process, you can have two antimetabolites. You can have this, which is indirectly have cause influencing the system because it is blocking that enzyme, and therefore the enzyme does not give you the methylene. And you have also this one that's directly blocking the enzyme, and therefore, although you have your deoxy UMP, so you have formed your deoxy UMP, but now the deoxy UMP requires the thymidylate synthetase enzyme, but that thymidylate synthetase enzyme has been blocked by 5-FU. And therefore, so this we can say is what we are calling sequential blockade. You are blocking, of course, not you are blocking the same pathway. Yes, you are blocking the same pathway at two different points, and therefore making the drugs very effective, especially if you have given the drugs in combination. If you given the drugs in combination, there will be sequential blockade, blocking of course, there are different enzymes, but in the same pathway. And so blocking different enzymes in the same pathway at different points, and therefore bringing about synergism, or bringing about complete blockade, or bring about much, much higher efficacy of those drugs. Also, so we are still looking at the antimetabolites. So you can see we had looked at the hydrofolate reductase inhibitors. Here we have folate antagonists. We are still on the folate antagonists, and you can say methotrexate is an antimetabolite of folic acid. Remember, what does folic acid do? When you have folic acid binds the dihydrofolate reductase enzyme so that it is reduced. So now we are saying this methotrexate is an antimetabolite of folic acid because it has structural resemblance with folic acid. It will deceive the enzyme, picked up, pop, the process is finished. So it's an antimetabolite of folic acid, and methotrexate is structurally derived by, we looked at it, N-methylation of the para-aminobenzoic acid residue, PAMA, and replacement of the pteridine hydroxyl by the isosteric amino group. Remember, we said if you remember the structure, we can always go back there. That's just what we had mentioned and nothing new. If we go back, I think we should have gone ahead. Sorry, but I've got it ahead. I hope. Yes, I have it here. So if you look at it, we are saying the pteridine hydroxyl group, amino group. The N, this is the nitrogen of the para-amino benzoic acid has been methylated. So N-methylation of the amino group of the para-amino benzoic acid, and also hydroxyl replacement with amino group on the pteridine group. So it's the same thing we had mentioned. I'm only putting it in words. So that's driven by N-methylation of the para-amino benzoic acid residue. So replacement of a hydrogen with the methyl group, and replacement of the pteridine hydroxyl group by a biosteric amino group. Hydroxyl group and the amino group are considered to be biosteric, but they will have different characteristics in terms of acidity and basicity. An amino group brings about basicity. Hydroxyl group does not really contribute to either. So the conversion of the hydroxyl to amino group increases the basicity of the N3 and yields greater enzyme affinity. So because it's an amino group, is an electron donor, or it's an electron donor or a proton acceptor, and therefore it is basic in nature. And that basicity gives the enzyme greater affinity, gives this molecule, greater affinity for the enzyme. When you have greater affinity, it will bind better, bind stronger. Once it binds, it stays a little bit longer, blocks that site, does not allow the proper substrate to bind. This drug competitively inhibits the binding of the substrate folic acid to the enzyme DHFR, resulting in reduction in the synthesis of nucleic acids and bases. So it will block the synthesis of the nucleic acids and bases. Remember, you require this for the formation of the imidalic acid. So that is a base. So therefore, there will be decrease in the synthesis of nucleic acid, specifically the imidalic acid, the conversion of uridylate to thymidylate as catalyzed by thymidylate synthesis. So it will block the synthesis of the nucleic acid bases. It will also block the conversion of uridine to thymidine as catalyzed by thymidylate synthesis. Purine synthesis is also inhibited. Why will purine synthesis be inhibited? Because you require this N10 formal tetrahydrofolic acid is a formal donor involved in purine synthesis. So you require the tetrahydrofolic acid to carry a formal group. A formal group is a CHO at position number 10. So remember, for synthesis of thymidylate acid, you require N5, N10 cofactor. For synthesis of purine, you require the N10 formal cofactor. But it must be joined to the tetrahydrofolic acid. You are not synthesizing tetrahydrofolic acid. You have blocked the synthesis of tetrahydrofolic acid. You will not have the N10 formal tetrahydrofolic acid. You will not synthesize your purines. The tetrahydrofolates are cofactors in at least 2 key steps in the normal biosynthesis of purines. In other words, we are saying these cofactors are also needed in the synthesis of the purines. They are needed in the synthesis of the pyrimidines, and ultimately, therefore, in the synthesis of the nucleic acids and in the synthesis of DNA. Once you block synthesis of DNA, you are going to affect the cell growth and division, and hence the drug will have brought about its activity. Methotrexate binds with the DHF, that hence caused pseudo-irreversible binding. So we have said that the amino group makes methotrexate more binding, more basic, giving it more binding. Gives it a higher affinity for the enzyme, for the dihydrofolate enzyme. And once you have that slightly stronger binding, it is like it is behaving as an antagonist a bit, but not completely. It will dissociate, but it dissociates very slowly. And that's why we are calling it a pseudo-irreversible binding. It's not completely irreversible, but the binding is much stronger between methotrexate and the dihydrofolate reductase enzyme compared to folic acid and dihydrofolate reductase enzyme. And therefore, that slightly stronger binding is what we are saying. It is almost bordering on irreversibility and therefore pseudo irreversible binding. The basis of this binding strength is the diaminopyrimidine ring, which is protonated at physiological pH. Remember, we said it has an amino group. This second amino group, so this is what we're calling the diaminopyrimidine ring. This extra amino group giving us the diaminopyrimidine ring, which of course is protonated at physiological pH, brings about a difference in the binding of that molecule and the dihydrofolate enzyme, and therefore allowing methotrexate to act as an antimetabolite, blocking the binding of folic acid and preferentially binding. And of course, once it preferentially binds, it binds strongly, it prevents the folic acid from binding, it stops the synthesis, as we have said, of the purines, stops the synthesis of the pyrimidines, and therefore ultimately apoptosis or death of the cell. That is indeed what we require. Acute lymphocytic leukemia. So uses can be acute lymphocytic leukemia, prophylaxis in meningeal leukemia, chronic carcinoma, and combination therapy for palliative management of breast cancer and osteocarcinoma. Some of the very adverse drug reactions, ulcerative stomatitis, leukopenia, and abdominal distress. So these are some of the uses of these drugs. These are some of the uses of these drugs. This was just to help us just to see the numbering of this numbering of this folic acid. This was our folic acid. So that's position number 1, position number 2, position number 3, position number 4. So this is the one we have. So position number 4, position number 5, position number 6, position number 7, position number 8. So this is the position, the oxo group, which you have said at position number 25. Sorry, up there. So at position number 4, sorry. The oxo group at position number 4 is the one you are saying is replaced in an amino group. So that is position number. So this goes up to 7, 6, 7, 8. And then 8, 1, 8, and then so 8 ends there. Then now we come to here 9, 10, 11, 12, 13, 14, 15, 16, then 17, 18, 19, 20, 21, 22, as this one there. And then after that, now you start, I believe, on the subsequent. Where is our 23? It should be a subsequent somewhere. Or is it an 22? There is 25, 24. Where is it? 23, 28, 27. It should be this one here. So 25, that is 24. This is 26, 26, yeah, 23 is here. So after number 22, so the whole folic acid basic molecule has 22 carbon atoms, and then the others are subsequent. So that's 22, that's 23. Very funny by number. Then you come to 24 there, 25. God. 26, 27, 28, 29. So this is just to have a rough idea. So when we talk about the 510, see, we are calling it 510 methylene tetra folic acid. It means the methylene group. Here is the methylene. It means when you call the 510, the methylene group is joined here. In between here. You know, the methylene group. So definitely you must lose this double bond here. So you must lose that double bond there. After all, you know, this is folic acid, and the folic acid is usually converted to the tetrahydrofolic acid. So the conversion to tetrahydrofolic acid, this is one of the double bonds that you lose. So this will have a hydrogen, and that you have a hydrogen. Remember, it's tetrahydrofolic acid. This is folic acid. So we don't have this bond. This has a hydrogen. This is having a hydrogen. So one of that hydrogen is removed, and you have formed that bond there. And that's what we'll be calling the N5N10 methylene, and then the tetrahydrofolate. And then, of course, we did mention the N10 formyl from synthesis of the purines. So when you need a formyl, remember, a formyl group means it's just here, that nitrogen. When you talk about the formyl, that nitrogen is joined to an aldehyde. That's the formyl. So that means this nitrogen will be bonded to a C double bond O. And you see, this, we are saying it is carrying the one carbon atom. So that's why we are calling it, even when you say it's N10. Was it N10 or N5? Formyl. So when you call it the formyl, it means at that position, one of the hydrogens has been replaced by an aldehyde group. And this aldehyde group, all its purpose is to carry this carbon. You see this extra carbon. So this group is added onto the drawing when the purine is being synthesized. And therefore, this group carries a carbon which is required in the synthesis of the purines. And if therefore you do not have the cofactor, the tetrahydrofolic acid cofactor, it means you do not have a carrier for this formyl group. If you do not have the tetrahydrofolic cofactor, you do not have a carrier for this methylene group. You require this methylene group to be added onto uracil to give you thymine. I hope it is clear. So we are saying base cofactors, very, very important as carriers. They are behaving as carriers. That is, you carry, you deliver, you go. But you see, the only difference, as we have said, is that as the folic acid goes back, or as it releases, the more it's carrying, it does not form the tetrahydrofolic acid. It's left as dihydrofolic acid. So it has to go back, first of all, into the tetrahydrofolic acid synthetic pathway, so that again it is reduced. So I hope that is very, very clear. We are saying these cofactors are indeed very important, because if they are not there, we will not get, when they are given as drugs, they will interfere with the synthesis of the purines and on the base of the bases. As we close, I'm going to look up what is the work of leucovorin. After all, you told me you've done this work. Why do we give sometimes leucovorin in combination with methotrexate? Why do we give leucovorin in combination with methotrexate? Just check it up. As I've said, I'm thanking God that I'm able to go through, but sometimes it's a struggle. So I hope you are understanding what we are doing. Going slowly, but once I recover, we move very faster. So just find out what is the role or the importance or the significance of leucovorin in cancer treatment. So the next one we look at now from there, we'll continue with the anti-metabolites, but I believe we'll be able to finish the anti-metabolites now next time, and even move on to the antibiotics. I hope we'll be able to do that. So are there any questions? Take them, but they work very slowly. But they will work ultimately. Do you have any questions, please? Are we okay? Any questions? So if there are no questions, can you sign in that you are there? Say present or okay, whatever. I hope. And of course, also let me know in case there are any challenges of understanding what we are doing, so that wherever we need to improve, we can improve. Sometimes, of course, as I have said, our bodies have challenges, especially in this weather. But do not be good forever. I'm also on medication. I went yesterday to the J Quarter Hospital on medication, so I should